So last class period, we saw some trig identities, and we're going to keep going into that. Going to keep leaning into that. There's lots and lots of trig identities out there. Some of them, like we saw last time, are worth knowing. Some of them are things we can derive from others. And last time we were deriving these trig identities, seeing which expressions were equivalent. And we had some tools to use. We had our basic reciprocal identities to use. We had our quotient identities that we could use. We had the Pythagorean identities. We had even oddness that we can use. And this time, in 7.2, we're going to look at the difference cofunction identities. Again. And these are actually very important identities for the next few other things we're going to look at. Okay? We call these the sum and difference identities. Now, basically, what you end up doing is you calculate cosine of alpha minus beta. All right? And it's kind of a long process of how you calculate that. I'll point out what's going on. I'm not going to do the whole proof of why it works the way it does. You can look that up on your own. There's videos out there that show you what that is. But I'll give you a gist of what the proof is. You look at alpha minus beta in two different ways. You create the angle alpha minus beta. That's the angle AOX on this picture. And then you do angle alpha and angle beta individually. And then POQ is also measured alpha minus beta. Everybody see that? So that means the distance from P to Q is equal to the distance from A to B. And when you do the calculations, what you get is you end up getting this top cosine identity that says cosine of x minus y is equal to cosine of x times cosine of y plus sine of x times sine of y. If you use a negative y instead of a positive y on the first, so you minus a negative y, that becomes a plus y here. Cosine of negative y would just be the same as cosine of y. Sine of y, sine of negative y would be the negative of the sine of y. So you use the even oddness to replace a minus y with a plus y. Okay. And then we've seen earlier that the sine function is just a shift of the cosine function. And so you can shift that identity in certain ways. Namely, if you shift over the sine function by pi over 2 units, you get the negative of cosine. You shift it to the right. If you shift over cosine pi over 2 units to the right, you get the positive sign. And so you shift those top two identities by pi over 2 units, and you get the bottom two identities. All right. That makes sense. Now, we don't actually have to memorize all 4 of these because you'll notice that with the cosine of x plus y, if I have x minus y, I could have just pretended I have a negative y instead of a positive y. Does that make sense? Just use the negative value. And the same thing with sine. So I have an x minus y equation and x plus y. I really don't need to know both of those, because replacing a y with a negative y gives me the other. Okay. So you see on the sheet, I didn't give all 4 of these some difference identities on the trig identity sheet that I handed out. I only gave 2 of them, and you can figure out the other 2 by just replacing with a negative. And then it turns out, if you take sine of x plus y, divide it by cosine of x plus y, you can do some algebraic manipulation and get the tangent sum identity. And if you want to find a tangent difference identity, just replace the y with the negative y. Okay. Again, this is also on our trig identity sheet. Makes sense? These are very important identities. These actually are going to generate a lot of the other identities that we're going to look at in the next few sections. Okay, so these are kind of like the Pythagorean identity. These are kind of some of the base identities that we have. Now, based on what we know, based on this sum difference identity, let's see if the following statements are true. If I take cosine of an angle plus pi, do I get cosine of that angle back? If I take cosine of x plus 3 pi over 2, is that the same thing as sine of x? So we're looking at if these are true or false. Okay. Well, there's multiple ways of doing this. One is by observing the graphs of the function. You can see if the shifts are correct and things like that, if they match up. But the easier way is just to say some identity on cosine. The left-hand side is cosine of theta times cosine of pi. I'm using the sum identity here, minus sine of theta times sine of pi. And then we have to know what cosine of pi is. We have to know what sine of pi is, but that's easy to calculate on our calculator. That's also easy to know on the unit circle. Cosine of pi on the unit circle. Well, if I'm at pi on the unit circle, the terminal angle shoots through the point -1, 0. Terminal side of the angle shoots through -1, 0. Everybody understand what I'm saying there? So cosine of pi is -1. So I get negative cosine theta there. And sine of pi is 0. Notice that becomes 0, and I get negative cosine of an angle is equal to cosine of that angle. That is false for most angles. Or false in general. So since this one was false, my original was false. Notice, however, if I would add negative cosine, it would have been true. Let's do this one in a similar way. We'll take cosine of x times cosine of 3 pi over 2 minus sine of x times sine of 3 pi over 2. Is that equal to sine of x? Well, 3 pi over 2 has terminal side pointing down, going through the point 0, -1 on the unit circle, right? So the cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is -1. Let me write that down. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. This becomes 0. This is the negative of -1, so that's positive sine. And therefore, that's a true identity. That actually is a true statement. Cosine of any value of x plus 3 pi over 2 is going to be the same as sine of that value of x. Interestingly enough. I want you to try to do these 3 using simplifications that we know. Remember, we know where pi is on the unit circle. Pi has terminal side going through -1, 0, 2 pi, 1, 0, pi over 2, 0, 1. Okay. Try to take sine of alpha minus pi, tangent of x plus 2 pi, and tangent of x plus pi over 2, and see what happens in each of those cases when you put them into the sum difference identities. When you rewrite them using sum difference identities. That's one. Doesn't match. But it doesn't exist. All right, so let's go through, or I'll start going through what these sum difference identities give us. So we have sine of alpha minus pi. I'm going to use the one on the formula sheet, and alpha will be the x value, negative pi will be the y value, all right, on the formula sheet. So the formula sheet says take sine of x. So in this formula, that's sine of alpha times cosine of y, that's negative pi. plus cosine of the x, in this case that's alpha, times sine of the y value, which is negative pi. So that's what we're looking at in this case. Now, if you wanted to use even odd identities right now, cosine of pi is the same thing as cosine of negative pi. That's fine. Or you could just think back to the unit circle. When we talk about the angle of pi, we're shooting backwards. If I talk about the angle of negative pi, I just have to rotate the other direction and shoot that same direction, right? So I get negative 1, 0 either way. So the cosine of negative pi is negative 1. So we have sine alpha times negative 1 plus cosine of alpha. Sine of negative pi is 0. So sine of alpha minus pi is negative sine of alpha. That makes sense? And that would be the end. That's all we're doing. Now, if we do tangent of x plus 2 pi, since we have tangent, I'm going to use the tangent identity. It says take the tangent of x plus the tangent of y divided by 1 minus the tangent of x times the tangent of y. In this case, the x is x and the y becomes 2 pi. So we just replace that y with the 2 pi. And then if you type in tangent of 2 pi on your calculator, you'll get 0. It's the ratio sine over cosine. 0 over 1 is 0. Okay. So we end up with 0. So that's tangent of x plus 0. I'll write the steps. Divided by 1 minus tangent of x times 0. This is just going to be tangent over 1, which is tangent. Oh, that makes sense. Does that make sense? By the way, well, I'll go back to that. I'll come back to all these in a second. Let me do the last one first. The last one before we go on. Now, if I try to do that same thing with tangent of x plus pi over 2, what happens is if I try to use this formula gives me problems. Because pi over 2 puts me at this point on the unit circle, and I'd be taking 1 divided by 0 when I take a tangent of pi over 2. So pi over 2 was one of those asymptote spots for tangent. If you remember the tangent function, pi over 2 is one of those asymptote spots. That does not mean tangent of x plus pi over 2 doesn't exist all the time. It just means this formula is useless in this case because we landed on one of the tangent spots with the pi over 2. Okay. So the formula doesn't work. This formula doesn't work. Because the domain doesn't work with pi over 2, right? But that doesn't mean this expression doesn't exist. Like if I plugged in 0.13, I could take tangent of 0.13 plus pi over 2 on my calculator and get it out a number. Okay. Or whatever other number I wanted to plug in, as long as it doesn't land on the asymptote. So you can plug in lots and lots of values for x and make this work. So what you could do instead is rewrite this as sine of x plus pi over 2 divided by cosine of x plus pi over 2. Because that's what tangent is, right? So you could have used the quotient identity and then use the sine over cosine sum difference identity. Sine, just like we did over there, is going to be sine of x cosine of pi over 2 plus cosine x sine pi over 2 and then all divided by the cosine version of that, which is cosine 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 of x times cosine of pi over 2 minus sine x sine pi over 2. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. So I replace each of the cosines with 0. I'll get rid of all that. This term, get rid of that term. And then the sine is 1. So notice what I get. Well, I'll do 2 steps. 0 plus cosine of x times 1, 0 minus sine of x times 1. So we get cosine over negative sine, which is negative cotangent of x. Does that make sense? The negative cotangent when you shift tangent over pi over 2 units. Again, it's always, when we talk about these things, it's always for values that you can plug in to the domain. All right. Now, we saw these shifts, I call them shifts, utilizing, we saw these identities utilizing the sum difference identities. We actually could have figured some of these out utilizing the graphs that we looked at in section 6.3. So for instance, if I were to do f of x is equal to sine of x, we have that graph. Now let's shift that. We had sine of alpha minus x. I'll just do x. Let me speak. Sine of alpha minus pi. So let me just do x minus some shift. I'll call the shift S. If I shift by pi units, notice what I get. I just get a flip across the x-axis. I get the negative of the sine of x. You see that? Do this. That. And you can see that if I shift it over 2 pi units back on top of the graph itself of sine, another way to say that is we have a period of 2 pi, right? We knew that earlier for the sine function. But if you just shift by about pi units, that gives you the opposite of sine, as we can see there. In a similar way with tangent, we can do shifts to tangent. Did we subtract or add? I added, so let me do a plus. See what's going on there? If I shift over, that would be about 1.57 is about pi over 2. I will do that. Shift it by a positive pi over 2, I get that. And if you were to graph cotangent, let's do H. So that's the graph of cotangent there in purple. Notice that if I flip across the x-axis, again, I get tangent of x plus pi over 2. And then lastly, if I shift over 2 pi units, I'm back onto itself. That was the tangent of x plus pi. 2 pi is equal to tangent of x. So we could have seen a lot of these shifts utilizing the graphs of these functions too, but it's a lot more efficient to know these sum difference identities in these cases and use those. By the way, if you ever encounter something like a secant or a cosecant, the way we're going to do those is very similar to the way I did tangent of x plus pi over 2. I'm going to rewrite those in terms of sines and cosines. Let me just go ahead and do it. So secant of x minus pi over 2. And then we have cosecant of pi minus x. Better. So I write this as 1 over cosine of x minus pi over 2. And then I use the sum difference identities on that. Cosine is cosine, cosine minus sine, sine. So cosine x cosine negative pi over 2 minus sine x sine negative pi over 2. Negative pi over 2 gets me at 0, -1 on the unit circle. So cosine is 0, sine is going to be a -1. Okay. So what I end up with is 1 over, this becomes 0. This is 0, 0 times 0. I get negative times negative. This is a -1 times a negative out here. That's going to give me a positive sine of x, which is the same thing as cosecant of x. That makes sense? 1 over sine is cosecant. There we go. Similarly, with cosecant, that is 1 over sine. And then I can use the sum difference identity for sine. Sine is sine cosine plus cosine sine. So sine pi times cosine of negative x plus cosine of pi times sine of negative x. Pi is over here on the unit circle. Therefore, cosine of pi is -1. Sine of pi is 0. So this part turns into 0. I get 1 over, this is again 0. This is -1. So it's -1 times sine of negative x. The odd nature of sine is an odd function. I can pull the negative out front and it'll cancel. And I end up with just 1 over sine of x. There's also cosecant of x, right?
Wouldn't sine be the y value of it?
Did I say that? Oh, yep, I did screw that up. I messed it up, didn't I? Thank you. I did something was off there. I screwed that up. Yeah. Cosine. Wait, no, did I?
I don't know.
Sine is the y value, so that's 0. Cosine is the, yeah, did I write that right?
Yeah.
Okay, so yeah, sine should be 0, so that becomes 0.
Oh,
This becomes -1 times sine of negative. Okay, I get it. Yeah. So there we go. Yeah, we're good. There we go. By the way, notice that means these two things are equal. Okay. Another way you could have checked your answer is you could actually have graphed this one and then graph this one and see that they line up everywhere. Everywhere their domain exists. So everywhere where we don't have asymptotes. But You can always, check, plug those both into your graphing calculator or plug those both into Desmos and see what happens. We can do this a lot. We can do this with essentially any version of like pi over 2 or pi or 3 pi over 2 or negative pi over 2 or negative pi or 2 pi. And sometimes people put these as separate identities, which we call cofunction identities. Those are also on your trig identities sheet. Or at least some of them are, not everyone. So cosine of pi over 2 minus x is actually the same thing as sine. If I take cosine of x plus pi over 2, I get a negative sine of x. And then if I do a similar thing with cosine and reverse the roles, sine of pi over 2 minus x is cosine of x. And then sine of pi over 2 plus x is the positive cosine of x. Okay. So if you plug in pi over 2 minus x, you get the positive version of the other. If you plug in x plus pi over 2, one of them gives the positive version, the other gives the negative version. And this again kind of comes from just the shifts. If we're thinking about how to shift things and how even odd functions work, this is what happens. I don't like these are fine to know. Okay, but they can always be derived from the sum difference identities, like you just saw us doing. And so I don't commit these to memory or anything like that. I don't give them any special treatment. Sum difference identities give you these in a straightforward manner. Okay. There's also tangent and cotangent cofunction identities. And you can see those on the screen as well. And you can see those on the trig identities sheet. Sometimes knowing these can simplify a process like these two cases. In this case, we're asking whether the following statements are true or false. It says cosine of x minus pi over 2 times sine of pi over 2 minus x is equal to cosine of x times sine of x. And then we have a cotangent pi over 2 minus theta. Times sine pi over 2 plus theta equals negative sine of theta. Now, if I wanted to, I could do the entire sum difference identities on both this one and also this one. Okay. Or I could just know some cofunction identities. And if I look up the cofunction identities, sometimes that makes things easier. Okay, so that's all I'm saying on this example. I didn't actually give you the cofunction identity for cosine of x minus pi over 2. I gave you cosine of x plus pi over 2 was negative sine. X minus pi over 2 will give you a positive sign, right? So using the cofunction identity, shifting in the other direction gives me positive sine of x for this one. This one I did give, that's pi over 2 minus x inside of a sine. That is cosine of x. And sure enough, that saves me a lot of time in those special cases. So in these special cases, knowing the cofunction identities will save me some time. That's true, obviously. And so therefore this one's true. Everybody understand what I'm saying? Save time instead of using the sum formula here and then also the sum formula here. Again, I didn't give this one explicitly. I said when you add pi over 2, you get a negative sign. But if you that means a shift in one direction, left. If you shift in the right direction, you get a positive sign. In this case, cotangent pi over 2 minus theta. That's one that we were given. That's the tangent of theta. And again, pi over 2 plus theta inside of the sine, that was also given. That's pi over 2 plus x or x plus pi over 2. That's the positive cosine of theta. Tangent, remember, is sine over cosine. So these cosines are going to cancel each other out. And I get sine of theta is equal to the negative of the sine of theta. That's obviously false for arbitrary angles of theta, for most angles of theta. False in general. If I had a positive sign on the right, I would have true. Any questions about that? These things? Again, we could have figured this out by expanding using the, well, writing this as tangent. And then using the formula or writing this as cosine over sine using the formula. sum identities formula. Could use the sum identities here, but knowing these co-function formulas just saves me some time on occasions. And there's lots and lots of them. You can shift by pi over 2, shift by pi, shift by 2 pi, take pi over 2 minus the theta, pi minus the theta. I only focused on pi over 2, but you can imagine what happens when you shift by pi. Very similar things. Okay. Now, the last thing we're going to do with these sum difference identities is we can actually find exact values for certain angles that we didn't know how to deal with yet. If I can write an angle as a sum or difference of angles that I already know, then I can use my sum difference identities to figure out the exact value for an angle. Does that make sense? Angles that I already know are like pi over 6, pi over 4, pi over 3. Remember, pi over 6, we're getting 1/2 and root 3 over 2. Pi over 3, 1/2, root 3 over 2. Pi over 4, root 2 over 2. And then the standard 0, pi over 2, pi, 3 pi over 2, 2 pi, that kind of stuff as well. So what if I wanted to figure out like the cosine of pi over 12? Or the sine of pi over 12? Or 5 pi over 12? We'll do this. We'll do it with 5 pi over 12 and pi over 12. Okay. Does that make sense? Might as well write them all down now. I'll be back there. I think it will have enough room. Okay. So the goal is I got to figure out how to rewrite pi over 12 as a sum or difference of two angles that I know. Okay. And anybody know how to do that? With pi over 3, pi over 4, pi over 6. Okay. Well, a third minus a fourth is 12. Okay. 1/3 minus 1/4 is 1/12. So if I know that, pi over 12 is pi over 3 minus pi over 4. Think about this. If you had common denominators, you'd have to get 4 pi over 12 minus 3 pi over 12. I see that? You'd have to multiply this one by 4 on top and bottom, this one by 3 on top and bottom. Makes sense? Now that I know that, I can say, well, cosine of pi over 12 is the same thing as cosine of pi over 3 minus pi over 4. And now I can apply the sum difference formula for cosine with these two values. The sum difference formula for cosine is going to be cosine of pi over 3 times cosine of negative pi over 4 minus sine of pi over 3 multiplied times sine of negative pi over 4. Excuse me. And these are things that I could either look up on my unit circle, cheat sheet, or if you remember how decimals work and you know what you're expecting, you can always type it in, like cosine of pi over 3. If I type that in, I get 0.5 in my calculator. I know that's 1/2. Okay. So I know that's 1/2. If I type in cosine of negative pi over 4, I get a positive root 2 over 2. Again, you can type that in on your calculator and just look at the decimal you get and notice that it's that decimal. If that makes sense. Sine of pi over 3 is root 3 over 2. Sine of negative pi over 4 is a negative root 2 over 2. So the exact value that you get is square root of 2 plus square root of 6, all divided by 4. We could have easily typed in and got a decimal approximation for cosine of pi over 12. But this shows me that if I did actually need the exact value, I could find the exact value if I wanted to. We're okay with that? We're okay with the algebra that I did there? By the way, when in doubt, plug it into your calculator. Plug in cosine of pi over 12. And then plug in square root of 2 plus square root of 6. And then divide that whole thing by 4. And you'll get the exact same value as long as you're in radian mode. Use your calculators in radian mode. I want you to try. We already know that pi over 12 is pi over 3 minus pi over 4. So use the sum difference formula for sine to get the sine of pi over 12. And then think about how you would rewrite 5 pi over 12 and get like the cosine of 5 pi over 12. You don't have to do both, but actually, yeah, let's just do one of those. Is that right? We'll do cosine of 5 pi over 12 and then sine of 1 pi over 12. All right, let's go through this. This all makes sense, the process anyways. So, power 12, once again, is just power 3 minus power 4. So I know the combination of power 3 and power 4 that gives me power 12. Therefore, when I plug it into the sine formula, I get sine of power 3 cosine of negative power 4 plus cosine of power 3 times sine of negative power 4. We know what those are from the last thing we just did, but we also could look those up on a circle. We can type in to our calculator if I can recognize decimals, right? You guys know what I mean by recognize decimals. Like if you type this in, sine of power 3, you get 0.866, blah, blah, blah. And if you recognize that as root 3 over 2, no, root 3 over 2, then we're good to go. Cosine of negative pi over 4 is a positive root 2 over 2. Cosine of pi over 3 is 1/2. Sine of negative pi over 4 is negative root 2 over 2. And when I multiply root 3 times root 2, I get root 6. That's going to be over 4 plus negative root 2 over 4. So as an exact value, this is root 6 minus root 2, all divided by 4. Again, you can type that on your calculator to confirm that. By the way, it's also interesting that this number squared plus this number squared would have to give you 1, right? That's what the Pythagorean identity says. Sine squared plus cosine squared is equal to 1. So that's another thing you could check. That's kind of inefficient way to check, but it's another way to check stuff. That this number squared plus this number squared has to give you 1. Any questions about that so far? Now, to do a similar thing with 5 pi over 12, well, think of 5 pi as 3 pi added together with 2 pi. A lot of times when I'm deconstructing this, I'll do this step. So, let's think of 5 as 3 plus 2. And then 3 over 12 is the same thing as 1/4. 2/12 is the same thing as 1/6. So 5 pi over 12 is the same thing as pi over 4 plus pi over 6. And then if I want to find the cosine of that, cosine of 5 pi over 12 is going to be the cosine of the sum of those two angles, pi over 4 plus pi over 6. And then I turn to my cosine formula. Cosine formula is cosine times cosine of one angle times cosine of the other, minus sine of one angle times the sine of the other. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 6 is root 3 over 2. Again, you can check that either by looking at the unit circle or understanding decimals on your calculator. Sine is root 2 over 2. Sine of pi over 4, is root 2 over 2. Sine of pi over 6 is 1 over 2. I'll do the math in my head. This is going to give me root 6 minus root 2 on top, and then 2 times 2 gives me 4 in the denominator. So I get root 6 minus root 2, all divided by 4. Notice we got the same thing, right? Interestingly enough. We did some work on the count. If you did some understanding of the unit circle, you could kind of figure out why that is. I won't go into too deep. I won't go into details now. All right. Not worth it. Okay. Any questions about that process? Now, this only helps us when we can write our angles as sums of things like pi over 3 or pi over 6 or pi over 4 or pi, or, all of those versions, okay? So this only helps me in those cases. If I gave you something like some angle like pi over 13, you'd say, I can't write that in a very easy way as a sum of pi over 3 and pi over 4 and pi over 6. That's not going to have a nice common denominator. So we'd still be out of luck with something like pi over 13 or pi over 10 or et cetera, et cetera. But in certain angles, we can get the actual values now. Now, the last thing is something that I'm just going to mention. Because this is what we're going to do moving forward. We have this whole sheet of trig identities. It turns out most of the other trig identities come from the sum difference identities. Okay. A lot of the other identities you can actually find using the sum difference identities. So just for example, think about what would happen if I wanted to do cosine of 2x and create an identity for that. Oh, wrong side. Or sine of 2x. Or cosine of 3x. We don't have an identity for cosine of 3x, but we could create one. It'd be complicated. Or tangent of 2x, or cotangent of 2x. Notice that these all on that trig identity sheet are listed under the double angle identities. Okay. And let me do the sine of 2x and show you where those come from. Those double angle identities come from. Okay. Sine of 2x is the same thing as the sine of x plus x. All right. Now that I write 2x as x plus x, I can use the sum difference identity where the x and y values are just both x. Does that make sense? So using the sum difference identity gives you sine x cosine of x plus cosine x sine x. Well, since order of multiplication doesn't make any difference, that's 2 times the sine of x times the cosine of x. It's 2 copies of that. And that's the double angle identity for sine. Again, kind of like when we dealt with cofunctions, these can all be derived using the sum difference, but it's nice to have double angle identities handy. Okay. And then what if we had cosine of 2x? Well, again, think of that as cosine of x plus x. Using the sum difference, that's cosine x times another copy of cosine x minus sine of x times another copy of sine of x. This is cosine squared of x minus sine squared of x. Now be careful, that is not 1, right? Cosine squared plus sine squared is 1. That's the Pythagorean identity. Cosine squared minus sine squared is cosine of 2x. It's a double angle identity. By the way, you'll see some other other double angle identities for cosine. Those just come from the Pythagorean identity substitution. So here's one of the double angle identities. If I replace this cosine squared with a 1 minus sine squared, notice what happens. I get 1 minus 2 copies of sine squared. Okay, follow that. And in a similar way, if I keep this first one as cosine squared, but I replace sine squared with 1 minus cosine squared, This is going to be a -1 and then a plus copy of cosine squared. So I get 2 copies of cosine squared, then -1. So we actually have 3 different versions of the double angle formula for cosine, and they just come from the sum difference identity. And then replace the cosine squared with the Pythagorean piece, or replace the sine squared with the Pythagorean piece. You can do the same thing with tangent as well. When you look at the sum difference identity for tangent, you'll see if we have x plus x, we get 2 copies of tangent on top. And then 1 minus tangent times tangent, so 1 minus tangent squared on bottom, which is the double angle identity. Okay. By the way, if I wanted to do a double angle identity for cotangent, there's 2 ways to do that. One is to do a double angle identity for cosine over double angle identity for sine. So that's one way you could do that. Or you could just take the reciprocal of the tangent of 2x. So if you wanted to do a cotangent of 2x, you leave it as cosine over sine, cosine of 2x over sine of 2x, or just think of it as reciprocal of tangent. Either way is fine. Does that all make sense? Now this brings us to the next section, which is double angle and then also half angle identities. So as we just saw, the sum difference identities manipulated give us the double angle identities. These are them. And as you can see, that's exactly the same thing as we had written on the board. These are also on your identities sheet. Now, like I previously said, these can all be derived from the sum difference identities. So if this were a bunch of things to memorize, which it's not, you don't have to commit any of these to memory. The only thing you probably want to remember is quotient identities, reciprocal Pythagorean, and maybe the sum difference, right? All the other ones are derived from there. But knowing these allows us to a little bit more quickly determine if a statement is true, or a little more quickly rewrite a statement and simplify a statement. So if we have a scenario like this that says, is the following equation true or false? And it says cosine squared of x is equal to 1/2 times cosine of 2x plus 1. We could do that a little more quickly having known the double angle identities than just knowing the sum difference identities. Make sense? Now, on this one, every time we have a cosine of 2x involved, I have a few options of which identity to use. In this scenario, probably what I would do, since I see a cosine squared on the other side, I'd probably use the cosine of 2x is equal to this one, because this one already involves the cosine squared. So I would probably use that third one on the board in hopes that something either matches up or cancels out in a nice way. So cosine of 2x, I'm going to replace with a 2 cosine squared minus 1. 2 cosine squared of x minus 1. And then I have a plus 1 on the end. And notice this minus 1 and plus 1 are going to cancel each other out. I'll be left with 1/2 times 2 cosine squared of x on the right hand side. One half times 2 is 1, so we get cosine squared of x is equal to cosine squared of x. So that's true. And then I can move on. Are you okay with what I did there? Again, anytime I have cosine of 2x, I kind of have to pick the best one, best version. And in this case, this was the nicer version to pick. If I would have picked this one, it would have also came out just fine. I would have just worked a little bit different. Okay. It would have been just fine, it just worked a little bit different. Does that make sense? Makes sense why picking this one would be. This one would have been tougher. This one would have stunk, to be honest with you, but this one's not too bad. This one's pretty straightforward. This one's pretty straightforward too. This one's probably the most straightforward. This is probably the second straightforward. This one's probably the worst in this particular scenario. In other scenarios, this one would be the best. Any questions about that? So we have true or false. Now we can use these double angle formulas. Just as a brief note, if you were to have used this one, what would have happened is you'd end up with cosine squared is equal to 1/2 times 1 minus 2 sine squared of x plus 1. This 1 and this 1 would add to give you 2. And then when you multiply it through by half, 2 times 1/2 would give you 1. 1/2 times -2 would give you minus sine squared x. So you would have ended up with that. And then moving this over here on that side would have give you cosine squared plus sine squared is equal to 1, which we know is true. We get that? So you could have done the other way. You could have done that way too, but again, I think this way is probably the easiest. 2 paths diverge in yellow wood. Pick the one you like best. All right. Whichever one you like. I want you to try this one on your own. Use those double angle identity, or use the double angle identity to figure out if 1 plus sine of 2 theta is equal to sine of theta plus cosine of theta quantity squared. All right. So let's go through, we'll go through this one. Oh, quickly. So sine of 2 theta, the nice one about sine is there's only one formula for the double angle formula for sine. This is straightforward. Only one way you can do that. 1 plus 2 times sine of theta times cosine of theta. On the other side, when you square this, remember it's sine plus cosine times another copy of sine plus cosine. So you have to distribute. I'm going to do that. We're going to go sine times sine, that's sine squared of theta. We'll have sine times cosine, that's 1 copy of sine theta times cosine theta. Then I'll have cosine times sine. And then I'll have cosine times cosine. So I'll have cosine squared of theta. That same thing? Sure. Sine squared plus cosine squared can be combined. I'll put those together up front. Sine squared of theta plus cosine squared of theta. I'll put those up front. Sine times cosine is the same thing as cosine times sine, right? So that's 2 copies of sine times cosine of theta. And what do we know about sine squared of theta plus cosine squared of theta? That's 1 because of the Pythagorean identity. So this on the right-hand side is in fact 1 plus 2 sine theta cosine theta. On the left-hand side, I have the exact same expression. So this is true for all values of theta. So that's a true equation. Notice we used a few rules there. We used double angle formula. We also used Pythagorean identity. We also used some algebraic know-how of how to square a binomial. All that kind of good stuff. That make sense? I'm going to skip example 3. You can look that up on your own if you'd like. And let's just do example 4. Cotangent of 2x equaling 2 divided by tangent of x minus cotangent of x. Let's work through this one together. Most of the work will probably be done on the left-hand side of the equation, but maybe not. See? So what I would do is I would look at my double angle identities. We have a lot of cotangents and tangents here. So I could write everything in terms of sines and cosines of 2x, sines and cosines of x, but I think that's going to be more busy than writing things in terms of tangent. So notice that tangent of 2x is 2 times tangent of x divided by 1 minus tangent squared. I'm going to write it this way. Cotangent is the reciprocal of tangent. So tangent is the reciprocal cotangent. Cotangent, tangent to reciprocal. I know the formula for the tangent of 2x. I can just take the reciprocal of that formula, and that'll be the formula for cotangent of 2x. So I'm thinking reciprocal. I'm only writing this step so that we know what I'm doing there. Okay. So cotangent should be 1 minus tangent squared of x divided by 2 times the tangent of x. that all right? Now, there's many ways of seeing what's going on here. Right now, if you wanted to, you could cross multiply, simplify sides if you'd like. I think what I'm gonna do to make this easy on myself is I'm going to multiply the left-hand side by a fraction of cotangent of x divided by another cotangent of x. Now, here's why I do that. Cotangent and tangent are reciprocals. When I multiply them together, they give me 1. We got that? So what happens is on the top, I'm left with cotangent of x when I take cotangent times 1. And since one copy of cotangent will cancel out one copy of that tangent, I'm just left with one copy of tangent there. Okay, get that? Cotangent times tangent is 1. So tangent times tangent squared gives me 1 times a single copy of tangent. That tough? Not tough. The minus tangent of x. And then what happens on in the denominator when I multiply by cotangent is I just end up with 2. Cotangent times tangent is 1. 2 times 1 is 2. And this is a little bit easier of a fraction to deal with. It doesn't have all the squares. Doesn't have what we want, or it doesn't have as quite as messy of things. By the way, is this true or false right now? False. Yeah, it's gonna be false. This denominator is the negative of this numerator. So those two fractions are negative reciprocals of each other. And we're not always going to get the same value for all when I plug in x. So those are negative reciprocals of each other. So I'll just note that negative reciprocals are not equal always. In fact, they're never equal. Cancel out the always. Put it that way. You could have also, if you wanted to, multiply everything out. Simplify, do all that too. But at this stage, just knowing that these are negative reciprocals of each other shows me that they're not equal. So the statement is false because of that, and then this is false as well. But if I had the negative reciprocal of this fraction, it would have been true. Any questions about that? By the way, this shows you different ways you can write the double angle identity for tangent as well. If you just multiply the top and bottom by cotangent, you'll get 2 over cotangent minus tangent for your double angle identity for tangent. And if you multiply top and bottom by cotangent squared, you'd get 2 cotangent divided by cotangent squared minus 1. Does that make sense? So there are other versions of that double angle identity for tangent than the one that I wrote on that sheet. That's all I'm getting at. Another way we could have used double angle identities is you could rewrite something like sine of 4x. You could rewrite something like cosine of 4x. When you do that, be careful that you're using the appropriate identities. Sometimes people make mathematical mistakes, right? False statements, because they think that if you put a 4 in front of the angle, that it does the same thing, or it's going to act the same way as putting a 2 in front of the angle. So sometimes people will mistakenly say, well, sine of 4x has to be 4 times sine times cosine. That is not the case, right? That is not true. Or people will say cosine of 2x is going to be like cosine of 4x is going to be like 4 cosine squared minus 1. That is not true. Okay. Neither of those things actually works. So we can't just replace the value of 2 into double angle identities when we have something like 4x. Can't replace the 2 with the 4, the same thing. What we have to realize is that 4x is actually 2 multiplied times 2x. And so I can think of this 4x using one double angle identity I can write that as sine of 2x times cosine of 2x. Now, if I want to break the arguments so that the arguments only involve the angle x, what I would have to do is I have to do another step where I do the double angle identity for sine here. And then I do one of my double angle identities for cosine here. I'll do the one with double angle identity for cosine. I'll use the cosine squared minus sine squared. So this gives me 4 sine x cosine x, and then I have to distribute that into this. So you'd end up with 4 sine x, and then the cosine x would be multiplied by cosine squared. That would give me cosine to the 3rd. Is that too fast? Or are you guys okay with that? Sine cosine times sine. Sine cosine times cosine squared gives me sine cosine to the 3rd. Sine cosine times sine squared will give me sine to the 3rd cosine. So that is the identity for sine of 4x, written in terms of the argument x. In terms of trig functions whose argument is x. Notice it's not the same thing as 4 times sine times cosine. That's all my point was. And if you try to do this for cosine, well, 4x is double 2x, so you'd have to do cosine squared of 2x minus sine squared of 2x. I'm going to write this out a long way. Cosine of 2x times another cosine of 2x minus sine 2x times another copy of sine of 2x. Gonna get nasty real quick, right? Then I'd have to do a double angle for cosine, another double angle for cosine, double angle for sine, double angle for sine, if I wanted to write this all with trig functions involving argument x. I'll go ahead and do that. So I get one copy of cosine squared of x minus sine squared of x, and then another copy of cosine squared of x minus sine squared of x. And then this one, I end up with 2 sine x cosine x, and then another copy of 2 sine x cosine x. Now I'm going to combine out some like terms and do all that kind of stuff. If you multiply this out, what you'll get is cosine to the 4th of x. You'll get one copy of cosine squared minus sine squared times minus sine squared, excuse me. So negative cosine squared times sine squared. You'll get another copy of negative cosine squared sine squared here. So you get minus 2 copies of what I'll call sine squared of x times cosine squared of x. And then negative sine squared times negative sine squared will give you a positive sine to the 4th. Notice what this will be. This will be 2 times 2, that'll be 4. And then I'll have sine squared, cosine squared again. So I'll have minus 4 sine squared of x, cosine squared of x. So what's this? This is cosine to the 4th power of x. This and this combined to give me minus 6 sine squared cosine squared of x. And then we have a plus sine to the 4th of x. Again, not a very nice formula for cosine of 4x. So the double angle formulas are pretty nice, but if we try to develop formulas for like 4x, 4 times an angle, those get pretty ugly pretty quickly using this technique. that right? It's pretty ugly pretty quickly using that. And you can imagine if I had like 8x, then you'd have to do a whole another operation, which would be even more complicated. So what I'm saying is that these don't expand in a very easily done way. All right, things start getting more complicated when your argument becomes 4x or 6x or 8x or even 3x. Okay. That makes sense? Now, the last types of identities in these sections are called the half angle identities. These all involve square roots. And they say if I have the sine of x over 2, then the value of that will be plus or minus the square root of 1 minus cosine of x divided by 2. The second one with cosine does almost the identical thing, except we have 1 plus cosine of x in the numerator rather than 1 minus cosine of x. And then tangent, you can think of as sine over cosine. And if you take those two values and divide them, you'll end up with 1 minus cosine of x divided by 1 plus cosine of x and take a square root of the whole thing. But I want to take a stab at where these come from. Well, these come from our double angle formulas written in reverse. Okay, specifically the two with cosines. Cosine of 2x. Let me explain what I mean by that. So we have that cosine of 2x was cosine squared minus sine squared. That's one of them. But we also had cosine of 2x. I want to make sure I get this right. Is 2 times cosine squared of x minus 1. And we had cosine of 2x is equal to 1 minus 2 times sine squared of x. So those are two of our formulas. Okay. Now just think of x being replaced with a theta over 2. So instead of using the letter x, I'm going to use the letter theta over 2. Angle by 2. If I put that into this, 2 times theta over 2 will give me cosine of theta. And I can just solve for this cosine of the half angle. So I add 1 to both sides, giving me cosine of theta plus 1 is equal to 2 times cosine squared of theta over 2. Dividing by 2 would give me cosine of theta plus 1 all over 2 is equal to the square of cosine theta over 2. In order to solve this, what would I do? I take plus or minus the square root of this side is cosine of theta over 2. So plus or minus square root of this side is the cosine of theta over 2, and that's my half angle formula for cosine. Doing the exact same thing over here. You subtract 1 and then divide by -2. And then take plus or minus the square root of both sides. You get the half angle version of sine. Okay. And then tangent is just sine over cosine. So this square root divided by this square root gives you 1 minus cosine over 1 plus sine in the denominator. Or 1 plus cosine. Gives me the tangent formula. Look at that. We get square root of 1 minus cosine theta over 1 minus 1 plus cosine theta. Get a little tongue tied there. There. So you get all of these just through rewriting your double angle formulas and solve it. Okay. Specifically those two that involve cosine of 2x. And we could ask similar things. We could say, is the tangent of theta over 2 equal to sine of theta divided by 1 plus cosine of theta? Now, these, I should say, these get a little bit tricky because of the plus or minus version of the square root, right? So it's a little bit involved, but it's not too crazy. What I do is I just say, on this left-hand side, let's use the positive square root, 1 minus cosine theta divided by 1 plus cosine theta. Is that equal to 4? So we can say plus or minus here. We'll just leave it as the positive version. We'll say it for a lot of values of theta. Any idea how we would maybe do that?
Square both sides.
We could square both sides. Square both sides. Get rid of the square root. That's one way to do it. And if you did it that way, you probably could get something. You get it to work. I'll put it that way. Square both sides, that'd be fine. You can get it to work. Do I want to square both sides yet? I don't think I want to square both sides. I'm gonna do it a different way. Okay. I'm going to take this square root. And on top and bottom of the fraction, I'm going to multiply times 1 plus cosine of theta. Now, the reason I do that is because when I do that in my denominator, I get 1 plus cosine of theta quantity squared. And when I take a square root of that, I get the same denominator as over here. Let's see where I'm going with that. Okay. I'm not saying that this is the only path. I'm just saying this is the path that I'm going to use. Again, squaring would have been a perfectly fine path to take. But what I'm going to get is the square root of 1 plus cosine of theta, quantity squared in my denominator. And then when I take the square root of that, I get the same denominator over here. That's why I wanted to use that. Now let's multiply. 1 times 1 gives me 1. We get a plus cosine theta and a minus cosine theta that would cancel each other out. And then I get minus cosine of theta squared. By the way, at this point, you can square both sides too, not a big deal. Okay. What I'm going to do is I'm going to realize that 1 minus cosine squared is the same thing as sine squared. Using my Pythagorean identity. Okay with that? So using my Pythagorean identity, the numerator becomes sine squared. The denominator becomes 1 plus cosine theta, quantity squared. If I take the square root of squared things, I either get the positive or the negative version of it, right? So again, we'll assume positive. And I get true state. And we're done. That's the whole thing. That's a true state. Again, this is not the only path you could have taken. You could have squaring would have been just fine right here. Squaring both sides. Seeing then what happens. And then you get rid of the square root early. I got rid of the square root late. But if you want to get rid of the square root early, you can square both sides, and then you could have done that same trick. Multiply both sides, top and bottom, by 1 plus cosine theta to get common denominators. Either way. So that one's true. Now I should say this. I should say the following. When you're doing this, it might depend on what quadrant you're in, whether this thing is true or not. We ignored the plus and minus. All right. And we squared both sides at some point, or took a square root of a square at some point. All right. So if that angle theta happened to give me some negative values in one version and positive values in another version, I might be getting the opposite. Like this might be the negative value of this. And so it might depend on exactly where theta lands, whether or not we have an actual true statement for all theta. But there will be a lot of theta that this will work. A lot of values that this will work. Does that make sense? So I'm going to ignore where the plus minus is for the most part, and then move on. Okay. We'll pick back up here next time. Obviously, we did not get through all of 7.4, so I'll delay that homework till next week. We'll do some more examples of this next time. There's not that many examples. I was just trying to show you how many there are. Just a couple of examples. We can find some exact values as well using these methods, using double angles and half angles and things like that. And then we'll move on to the last couple of sections of chapter 7. Okay, so that's what we'll do next time. And but you'll still have to complete the 6.3 homework and the 7.1, 7.2 homework. Okay, make sense? All right. I will see you all next time.